Now that we've defined sine on the unit circle for all angles, we can actually sketch a graph of the sine function on the real line. Here I have the axis marked with radians, so we'll do this in radian measurement. So to start with, going back to the unit circle, we define sine to be the y values of all of these points. The points I'm going to use are these ones, the ones that fall on the axes. And against the y values of these points that I'm going to plot to get my graph of the sine function. So let's start with 0 radians if we're right here. So 0 radians would be right here on the x-axis. The y value of this point is y is equal to 0. So that means for sine at 0, it equals 0. All right, so if we rotate all the way up to here, in terms of radians, we are at pi over 2. And the y value of this point is going to be on the graph of sine. And here the y value of this point is equal to 1. So at pi over 2, I'm going to plot the number 1. Continuing around the circle, this takes me to pi radians. And the y value drops back down to 0. So over here at pi, I'll plot 0. Continue around to 3 pi over 2. At this radian measurement, the y value is now -1. So at 3 pi over 2, I will plot -1. And then when we rotate from 3 pi over 2 back up to here, that's 2 pi, we are back at y is equal to 0, and so we get this point back. So this was back to 2 pi. As we continue to go around this circle again, we get the same values 0, 1, 0, -1 back over and over again. And that means we get this shape repeated forever going in this direction. Let me sketch in the graph of sine. The graph looks something like this. This is one cycle of sine, and it will repeat forever in both directions. And we call this one cycle the period, and it has a length of 2 pi. So that's how long it takes to go from 0 back down here until you get to 0 again. Now, what if you were to start at 0 radians and go backwards? So like what's happening over here on the graph? It's worth labeling that too. But if you're starting here at 0 and you go backwards by pi over 2, this spot right here is really negative pi over 2. It's the same location as 3 pi over 2. However, on this graph, what's going to happen is when we go back to the angle of negative pi over 2, the y value here is -1, so that is the point that I will plot. If we rotate back here, this is going to be the location of negative pi, and then the y value is back to 0, so I can plot 0. If I go to -3 pi over 2, which is up here, now the y value is back to 1. And if I go backwards one full rotation, this is also the location of -2 pi, and we're back at a y value of 0. If I connect these, you get the same curve. So let's note that this goes forever in both directions. One other thing to point out is something called the amplitude. This is how far the graph is from the x-axis. So like the furthest that the sine function goes from this axis, well here at pi over 2 it goes up to 1. 1 is the furthest point away. And over here, well the y value is down at -1, but in terms of how far it is away as a distance, it is also a distance of 1. So this is what we're going to refer to as the amplitude. And in this case, it's going to be equal to 1. If you know the basic shape of the sine function, you can use that to graph more complicated versions of it, like this one. Y is equal to 3 sine of 2x. What does that graph look like? I'm going to start this by sketching on a graph of the sine function. So like the original one started here at 0, 0, then it went up to 1, back down to 0, down to -1 before returning back to this point here at 0. And I'm just using this as a reference, so I'll just sort of like put in a dotted line here. And maybe I'll do the same thing going back in this direction. So let's see, at negative pi over 2, it was -1. Then it returned to 0. It went up to +1 before returning back to 0. And so my sine function, again, I'm just putting this as a reference, looks like this. So in red, that is sine of x. The period is 2 pi, and the amplitude is 1. So what would this graph look like? 3 sine of 2x. There are two changes between this function and this one. So the two changes that I see, I'll list them down here, is, okay, we have this 2 being multiplied to the x. I know since we're multiplying this x by a 2, it'll have the opposite effect on the x values on this graph. So it's actually going to take half of each x value. The second change in this function here is the 3. This 3 is being multiplied to the y values on this sine function. That's going to have the effect that you would expect, where we're going to multiply the y values by 3. So what I'll do is, I'm going to look at this graph, and I'm going to run it through these two steps in this order to see how the points on this original function look on this brand new function. We'll get a similar looking curve, but the points are going to be in slightly different locations. Let's start with this point here, the point 0, 0. Well, the x value is 0, and so if I take half of that x value, it does not go anywhere. Second step is to multiply the y value by 3. The y value is 0. So on this new curve, the point 0, 0, it actually doesn't go anywhere. So I'll just put, well, that point stays right where it is. What about this point? This is the point x equals pi over 2 with a y value of 1. Well, if we take half of this x value, half of pi over 2 is going to be here, which is pi over 4. So this is going to be the location of the new x value at pi over 4. And the y value is currently 1, and if you triple it, it's going to go up to 3. This point goes to pi over 4, and then it goes up to 3. So this is not enough to get an entire graph of the function, but let's keep going. This point here, if we take half of the x value, it goes to pi over 2. And the y value here is 0, so it actually stays at 0. So this point stays right where it is. Okay, at this point, if I take half of 3 pi over 2, that's going to be 3 pi over 4, which is here. The y value is -1, so we're going to multiply it by 3 to get -3. This point goes to 3 pi over 4 down to -3. And I guess lastly, this point, half of 2 pi is at pi. The y value is at 0. If we triple it, it stays at 0. I think this is enough to sketch what's happening on this part of the function. We took half of all the x values and tripled the y values, and the resulting equation looks like this. Just a rough sketch. I'll put a ... to indicate that this thing is really going forever in this direction. We could do the same thing for the x values that appear over here. For example, this x value is at negative pi over 2. If I take half of it, it's going to go to negative pi over 4. Since the y value is -1, if I triple it, it goes to -3. So this point goes to negative pi over 4 down to -3. This has an x value of negative pi. Half would go to negative pi over 2. If I triple the y value, which is 0, it actually stays at 0. Similar thing happens to this point. Half of the x coordinate goes from -3 pi over 2 to 3 pi over 4. The The y value is 1, so if we triple it, it goes up to 3, it goes up here. And the last point is this at negative 2 pi, goes to negative pi when I divide by 2. The y value is 0, so it stays at 0, and so I get this. And if I sketch in the sine curve around it, I see a picture that looks like this. And this pattern continues forever to the left. So here it is. This is a sketch of what this new graph looks like based off of the original function here. So a couple of questions are, well, what's the period? How long do you have to travel to get one cycle? And what is the amplitude? If we start with the period, on the original sine function, you have to go from 0 to 2 pi to get one full cycle. But here, on the new graph, you have to go from 0 to pi to get one full cycle. So this means that the period is actually pi. So if we see a 2 here, it's actually going to be half as much on the new equation since we're taking half of the x values. That's the net result of putting a 2 multiplied to this x. The amplitude is how far the graph moves away from this axis. And this time the largest value is 3. We get negative 3 down here, but in terms of distance, we moved a distance of 3 away from this axis, so we will record the amplitude as 3. All right, now let's graph the cosine function. It'll be similar to graphing sine, but the only difference is we are going to use the x-coordinates on the unit circle instead of the y-coordinates. Again, we're going to use radians when looking at the graph. So if we start here at 0 radians and I look at this point, the x-coordinate is equal to 1. So 1 is the number that I actually want to graph. So at 0 radians, cosine takes on a value of 1, so I will plot 1 at 0 radians. If we move to pi over 2, at this point the x-coordinate is 0, so at pi over 2 radians, I'll put the number 0 for the value of cosine. When we move to pi radians, the x-coordinate is now negative 1, so I plot negative 1. When we get to 3 pi over 2, the x-coordinate is back at 0. And then we finally rotate back to 2 pi. We're back where we started, at an x value of 1. So if you connect these with a smooth curve, you get this. This is one cycle of cosine. You start at 1, drop down to negative 1 before returning back to positive 1. And this thing will repeat forever in both directions. So just like sine, the period of the cosine function is 2 pi. Of course, we could also graph cosine for negative angle measurements like negative pi over 2 and negative pi. To see that on this unit circle, if you want to get to negative pi over 2, you would rotate in this direction. So 3 pi over 2 and negative pi over 2 are in the same spot. And the x value here again was 0, so cosine of negative pi over 2 is 0. Going back here, this would be negative pi, and the x value is negative 1. If we go to here, this would be negative 3 pi over 2, and the x-coordinate is back to 0. And then when we return to negative 2 pi, we are back at 1. And so if we connect these points with a smooth curve, we get this. So it has the same shape, it's just going in the other direction. One last thing is the amplitude is also 1, just like with sine. And the reason for that is if you start on the axis, the distance that we'd have to go to get to this point, the one furthest away, is 1. And even though this is down at negative 1, the distance we would say is 1. And that is what we call the amplitude. All right, so let's use that graph of cosine to graph y is equal to cosine of x plus pi over 4. So what I'll do is I'll first graph y is equal to cosine of x. I'll put that on here as a reference. And the main points were, well, okay, at 0 it's equal to 1, at pi over 2 it's equal to 0, at pi it's equal to -1, and so on. So I'll put these main points on here like this. And then it's doing the same thing going in the other direction like this. So this is your main graph of cosine, amplitude of 1 and a period of 2 pi. There's only one difference between this function and this one, and there's x plus pi over 4. This is a transformation, and it's changing only the x values. So there is one difference on this brand new function. We're changing the x's. And it's x plus pi over 4, but we're going to have the opposite effect on the brand new x values. So this doesn't mean go right pi over 4. It actually means we're going to move all the points left by pi over 4. That's the only change. So I'll look at these main points, I'll move them left pi over 4, and then sketch the new graph. So let's start here. This is the point 0, 1. I know I'm moving it left pi over 4. Where's its new location going to be? Well, it's going to be at an x value of negative pi over 4, which is right here. If you take half of the pi over 2, it's going to be pi over 4. So that means I'm actually moving in this direction here. This is the new coordinate, so let me plot it. This is negative pi over 4 for the x value and 1 for the y value. Likewise, this point, okay, if this whole distance is pi over 2, half this distance is pi over 4. So if we go left pi over 4, this point moves right here. So I'll plot that point. Here, this is at pi. If I go pi over 4 in this direction, I end up here. So my new point is here. Okay, this one, if I go pi over 4 to the left, it's going to go here. And I have a point here. I'm going pi over 4 to the left. It's going to end up here. I could do that for all of these points. This one, if I go pi over 4 to the left, I go here. If this goes pi over 4 to the left, I'm here. Pi over 4 to the left takes me here. And this one actually is no longer on my grid, so I'm not really going to try to sketch it. But I do know what the final graph looks like. It's going to look like the cosine function, except it's going through these points. So I'm going to do my best to try to sketch that. So we get something that looks like this. So I could put I know this is continuing forever both to the left and to the right. So now that I have a sketch of the graph, what is the amplitude? What is the period? And what is this other term called the phase shift? I'll start with a couple that we probably already know. To begin with, what is the amplitude on my new curve? And it's equal to 1. We didn't multiply this function by anything, so that turns out to leave the amplitude alone. The furthest that this new curve is away from the x-axis is 1. It's up to positive 1 here. It's down to negative 1 here, and in terms of the distance away, we would just say it's positive 1. What about the period? This time, we moved every single point by the same amount to the left. That will have no effect on the period of this function. You still are going a distance of 2 pi to achieve one full cycle. So if there's no number in front of this x, that means the period must also be the same, which is 2 pi. This last term, which is something called the phase shift, this is how far does the graph move to the left or to the right. And when I see this pi over 4 here, I know the phase shift is going to be by that amount. It's going to be pi over 4. And we'll include a negative to indicate that, oh, well, it's actually moving in the negative direction. So this term is just how far did you move the graph, left or right? And we can determine that completely by this number here. It's negative because it's going to move in the opposite direction as the sign that appears here. In example 4, I want to graph the function y equals 2 cosine 2x plus pi. Here I have a graph of cosine sketched on that I can use as a reference. But what I'd like to do is figure out, well, what's the amplitude, what's the period, and what is the phase shift? If I look at the way this function's written, we probably can guess some of these answers already. Like, for example, this 2 here, I know that's going to affect the amplitude. This 2 will multiply 2 to every single y value. So I'm going to go ahead and write down that, well, I think the amplitude is equal to positive 2. The next thing, I see there's a 2 next to the x. I know this 2 is going to affect the period. If a 2 is multiplied to this x, the net result is that we're actually taking half of the x values. What does this mean about the period? Well, if the period on the original cosine function is 2 pi, and here we're taking half of all the x values, it should be that the period is actually pi. And the last thing is, well, what's the phase shift? Because of what's written here, I know the graph is going to move left or right. Well, the fact that it's a plus means, well, we're actually going to move left. It'll be the opposite of what I expect. But is it going to move by pi? And this is kind of confusing because, well, there's this 2 here that's affecting the x values as well. So to see how far it actually moves, what you can do is rewrite your function a little bit by factoring a 2 out from these first 2 terms. Here's what I mean. I'm going to write this as, well, it's 2 times cosine of, okay, if I take 2 out from here and here, I'll have x left over. I mean, that makes sense. 2 times x is 2x. But over here, I would have to put pi over 2. And the reason is, if you multiply this 2 to pi over 2, the 2's cancel and you're left with pi. Over here, it's a little bit easier to see what the phase shift of your graph is because you can ignore this 2 for the time being and focus on how you're changing just the x part of it. So yeah, we're actually going left, so I'll put a negative for my phase shift to indicate that it's a leftward movement, but it's actually going to go left by pi over 2. So we can actually graph this function just by using this information. Let's try it out. I still write down some notes, though, to guide me through this process. So there are 3 changes that are happening. The way things are changing within this function are, I'll first deal with this 2. So I'm going to take half the x values. Then I'll do my phase shift of this negative pi over 2, which is left pi over 2. And the last thing I'll do is double the y values. Let's try it out. Okay, if we take half of the x value here, nothing happens. The x value is 0, so it stays where it is. Okay, I'll go left pi over 2, so I end up here. Then, when I double this y value of 1, it goes from 1 up to 2. So this is my new point. Next, I'll work with this point. This is at pi over 2. If I take half of it, I get pi over 4. If I move to the left pi over 2, that's moving pi over 4 twice, and I'm here. I then multiply the y value by 2, but since the y value was 0, it stays right at 0. Okay, about this point. So first, I take half of the x value, so I go to pi over 2. I then do a phase shift to the left by pi over 2. I multiply the y value by 2, and it goes to -2. Okay, for this point, if I do half of the x value, I go to 3 pi over 4. If I move pi over 2 to the left, I end up at pi over 4. The y value was 0, so it goes at 0 after I multiply by 2. Now this point, if I take half of the x value, I go to pi. If I go pi over 2 to the left, I end up at pi over 2. And if I double the y value, I end up with 2. So I've used all of these points. I guess I'll complete it by using these as well. So for starters, okay, for this x value, first I take half of it, which is pi over 4. I then go pi over 2 to the left, which is here. I multiply the y value by 2, and it stays 0. Likewise for this one, I take half of the x value, that's negative pi over 2. I go pi over 2 to the left, takes me back to this negative pi, and if I double the y value, it goes down to -2. Same thing here. Half of this x value is -3 pi over 4. Pi over 2 to the left takes me here. And then if I double that y value, it actually stays at 0. And lastly, half of this one goes to negative pi. If I go pi over 2 to the left, I'm here. And if I double the y value, it goes up to 2. I can now sketch the function. And I'll just note that it goes forever in both directions. All right, so just to point out, I first dealt with the x values with the 2. I then went left due to the phase shift, and then I doubled the y values. So just to summarize these ideas, if you have a sine function or a cosine function of the form like a sine bx plus c, these numbers can determine the amplitude, period, and phase shift. So like for example, if you had y was equal to -4 sine of 2x minus pi, well here we're saying that a is equal to -4, b is equal to 2, and c is equal to -pi. If you want to know the amplitude, you take the absolute value of a, which in this case is the absolute value of -4, which is 4. The amplitude was the distance away from the x-axis, and it should be a positive number. For the period, it's 2 pi over b, and in this case would be 2 pi over 2, or pi. You divide by the number that's in front of the x into the period 2 pi for both sine and cosine. And lastly, the phase shift can be determined by computing negative c over b. And for this example, c is -pi and b is 2. The two negatives cancel to give you a positive pi over 2. And this is telling you that the graph is moving pi over 2 places to the right.